Hello, warriors. This is Miss Lemens coming at you. This is our fifth lesson, and we will be covering Gay-Lussac's law, which explores the relationship between temperature and pressure. So Gay-Lussac's law is showing us how temperature impacts pressure, or how pressure is dependent on temperature. It is a directly proportional relationship, meaning that as temperature increases, pressure will also increase. N and V are frozen, as in they are constant, so that's the number of moles of gas, and the volume in liters, they are held constant. Temperature is measured in Kelvin, which is symbolized with a capital K, and then the formula is P1 over T1 equals P2 over T2. So you can see in this image to the right that there is a cool gas inside a rigid container, meaning the container does not stretch like a balloon. Think of like a gas tank. And we subject it to heat. When we increase the temperature of that gas, we keep the volume and the number of moles the same. You can see that the kinetic energy of our particles increases. Remember, temperature and kinetic energy are directly related. Temperature measures the average kinetic energy of those gas particles. So if we increase the temperature, that means that the average kinetic energy of the gas particles is also increasing. And we show that by putting large arrows. So this has a shorter kinetic or a smaller kinetic energy, and it's shown by a short arrow, whereas this has a higher kinetic energy, and that's shown with a larger arrow. So as we increase the temperature, we increase the kinetic energy, which means that if you were to bounce this particle off of the wall or into each other, it's going to be more energetic or be more forceful. If you think about it, this particle is walking towards the wall versus this particle, which is running towards the wall. Running towards the wall and hitting the wall is going to be much more forceful than walking towards the wall and just bumping into it. So if we increase that temperature, we increase the kinetic energy, which means that these particles are going to be bouncing off the walls of the container with much more force. And because the container does not flex, it's a rigid container, then that means that the pressure is going to increase. Okay, so if the temperature increases, that means the kinetic energy increases, which means the particles are hitting the sides of the container with more force or more energy, which means that the pressure is increasing inside this container. So we can see that in this, really great graph here, that the only thing, there's not a lot of moving parts here, and that's because we have a rigid container. Notice that the volume of the piston chamber does not change, it stays constant. We're also not injecting any more additional moles of gas. We're keeping it constant. So I know that the particles aren't shown moving here, but you can see that as we increase the temperature, the pressure is also increasing. So if you were to imagine what's happening inside this piston chamber, you could envision these particles, as the temperature increases, to start rapidly vibrating more and more and more with the increase of that temperature. And this is the graph here that you should expect to see when we are evaluating the relationship between pressure and temperature. This is a direct proportion, and you would see it as such. So let's go ahead and take a look at the back of the last pages of your lab. Number 13 gives you two piston chambers. It says, the container below is filled with gas and sealed with a non-adjustable top. So this is a rigid container. The initial pressure of the container is 2 atm, and the temperature is 300 Kelvin. A person adjusts the temperature of the container 3 times. You use Gay-Lussac's law to determine the pressure at 3 different temperatures. Okay, so this is just the first part of this first question, number 13. So I'm going to start by using Gay-Lussac's law the equation of which is P1 over T1 is equal to P2 over T2. P1 and T1 being the initial piston chamber, and P2 and T2 being the second piston chamber after we've adjusted the temperature. So I'm going to go ahead and plug in the information that I know. I've got 2 atm divided by 300 Kelvin set equal to X, because we're trying to figure out the pressure, over 150 Kelvin. The first step that I'm going to do is simplify this fraction. And when I do that, I end up with 0.00666666 repeating equal to X over 150. Now, this is a little scary because we're looking at a fraction with X in it, so we need to get X out of that fraction. We're going to do that by multiplying both sides of this equation by 150 Kelvin. What that does is it cancels out 150 and gives us 1 equals X. Now, you can't leave your answer just as 1 because we need to pay attention to sig figs. This right here in the equation, this actually should say 2.0. The lowest number of sig figs is 2, 1, 2. This value and this value, the temperature values, both have 4 significant figures, and we only need the lowest number. So we would round this answer 1 to be 2 sig figs. That would look like this. 1.0 atm. All right, let's go ahead and find another one where instead of looking for pressure, we are observing temperature or solving for a temperature. On a different day, the person changes the pressure 3 times. Use Gay-Lussac's law to determine the temperature at 3 different pressures. Okay, so you can see here that we aren't given the initial container pressure and temperature just because it was given to us in the previous question. So 1.0 atm and 300 Kelvin. It's asking us to determine the temperature, which has been left blank for us underneath this piston chamber, and then at 3 different pressures. So I'm going to use Gay-Lussac's law. P1 over T1 is equal to P2 over T2. And we are going to plug in the information that we know. So that would be 1 atm divided by 300 Kelvin set equal to 0.50 atm over X. Okay, so now we need to go ahead and solve for X. The first thing I'm going to do is simplify this fraction. So 1 divided by 300 Kelvin equals 0.00333333 repeating. Set equal to 0.5 atm over X, right? I didn't do anything to the right-hand side of the equation, not yet. Now I need to. You can see that X is stuck in a fraction, and that's not good. So the only way we can get rid of that fraction is to multiply both sides by X. And I know that that can make people very uncomfortable, but if we multiply this fraction by X, X will be canceled out. If we multiply this side, the left-hand side, by X, what is 0.003333 repeating times X? It is 0.003333 repeating X set equal to 0.50 atm. So we needed to multiply both sides of this equation to get X out of the denominator. We do have one more step though, because X has not been isolated. So in order to get X by itself, if it's being multiplied by 0.00333 repeating, we need to divide both sides by 0.00333333 repeating. So when I do that, I end up getting the value 150.0150015 Kelvin. Now, that's a great answer. It's very, very precise, but we really don't need all of those significant figures. If you look back at the equation, we only have 2 sig figs in this number, 2 sig figs in this number, 4 sig figs in this temperature. So our final answer needs to be rounded to 2 significant digits, the lowest number of significant digits given to us. So our final answer should be 150, that should be Kelvin, not liters, so that is a typo on my part, but that'd be 150 Kelvin with a K. And there would not be a decimal point here because we only need 2 sig figs, and this 0 is not significant if there is no decimal point. If you guys have any questions about Gay-Lussac's law, feel free to reach out to me via email, Remind, or even set up a one-on-one Google Meet session with me. Best of luck to you, and remember, this is going to be due tomorrow night or Wednesday night at 11:59 p.m. Good luck.